Hello and welcome to this next lecture in our computational chemistry course. In this lecture, I am going to demonstrate the two interpolating methods. One is the Newton's interpolation and the next one is the Lagrange interpolation. We have discussed the formula in the last lecture, so I will not go too much into the formula again. Let us directly start with our execution of the program. So, now you look at our screen. On our screen, I am in a directory already in an interpolation directory. You look at the last lines here INTRP. I am in that interpolation directory. So, why did I create the directory? Let me go back to the previous directory cd dot dot, it makes me go to the previous directory and I do ls command lists me all the files in that program. See, there are so many files in that directory. So, when you have so many files, it is impossible to keep track of which file is where. So, in order to get around that problem, I have created two directories. One is the INTRP directory and the other one is the matrices directory. In the next lecture, I will be discussing matrices. So, I have created a separate directory where all the files related to matrices are there. The present directory has become very cluttered, and what are these? A dot out, B exec, exec dp, exec fs, these were the files that are executable files which we used to execute our earlier programs. Remember, A dot out is the default name for the executable file, whereas if you want instead of A dot out some other name, you have to change your G-Fortran compiler statement. When you change the compiler statement, you can write your executable file with different names such as exec fs, exec dp, exec cd, exec c as well as A dot out. You can change the names. So, now I have everything in my interp directory. So, I will go to that directory cd interp. So, this is the directory and I have already gone to that directory. Now, let us do ls minus l, ls minus l, that is ls space minus l. Remember the space, if there is no space it will give an error, ls minus l. So, it will give me all the files in the directory, the detailed details it will give you. Okay. There are several files of interest today are INTRPL dot f, this is a Lagrange interpolating polynomial file, and INTRPN dot f, this is a Newton's interpolation program. Dot f because it is an extension, it is a Fortran program. So, I will go to this INTRPN dot f, then we will look at all the details, compile and execute. Okay. Then there are some data files as well. What are those data files? INTRP.dat, that is one data file, NEWTINTP, this is a data file which is an output of that program. So, let me edit this particular file INTRPN.f. What is my command? VI INTERPN.f. So, this is my Newton's interpolation program. I have made some mistake. So, let me correct it INTERPN.f. So, I go to this. So, I have gone to this program. So, whenever I use that VI command, I am in the edit mode. If I want to insert thing, I have to type I and then it will start inserting. Okay. So, now let us look at this program again. I have looked at some lines in the last lecture already. So, first 6 or 7 are comment cards, it just said Newton's interpolating polynomial of degree 3, Pnx is equal to y naught and so on. Then for function fx in the interval x naught to xn, this is my interval. Interpolation polynomial is always in the interval between the starting value of x, x naught, and the last value which is xn. Okay. So, what is my algorithm? Read all the input, initialize the difference table, choose x and evaluate the polynomial for a large number of data points at a constant interval. Okay. Now, this particular interpolation method, there are n plus 1 data points and these points are at a constant interval difference. Okay. So, now this dimension statement x 10. So, there are 10 data points to be read. Okay. So, this is a one dimensional array with 10 variables in that dimension. So, y 10 again it is a one dimensional array with 10 values. then del y is my difference table. Remember we discussed first order difference, second order, third order. So, I collect all that in my difference table, then C is my coefficient table, these t, p n and x bar are all additional variables which I will not use right away. Okay. So, now go to this open unit equal to 8, file equal to interpol.dat, intrp.dat, this is my data file, and 12 open 12 file equal to quote newt newt intp quote complete bracket complete. Remember in an open statement, open left bracket unit equal to 12 comma file equal to single quote, then the name of the file, one more quote bracket complete. Any error will give you problems. Okay. Now, so then I have two format statements, okay, and I tried to execute this with format statements. There were some problems. So, I have avoided the format in the read statements. So, what am I going to read in this program? Read 8 comma star np1 comma m. np1 was 1 plus n, np1. So, if there are polynomial of order 3, then np1 will be 4 data points, and m is the number of points at which I want the interpolating polynomial. This m can be any number, m can be any number. So, these two I am going to read from my file 8. Star means there is no specific format. Okay. Then read 8 comma star xi yi I going from 1 to np1. In the last lecture I mentioned that whenever I give in bracket, okay, xi comma yi comma I going from 1 comma np1, it is an implicit do loop. It is as if I am writing a do loop, and in that do loop for each value of I am going to read xi and yi. So, this do I would have done do some 10 I going from 1 to npn, read xi yi and 10 continue. This is how I would be reading in that do loop. So, this is the same as a do loop. Then I am going to write whatever I read, I am going to write on the screen. So, write star comma 101 xi yi I going from 1 to npn. Now, 101 is a format statement. What is that format statement? Look at this 101 format 2e 10.3. What is this 2e 10.3? E 10.3 means it is a format, E format 3 letters after the decimal point. 0.3 means 3 letters after the decimal point. Total space will be 10 values, decimal point takes 1 point. So, there will be 6 values to write the number on the left side of the decimal. So, there are 2 numbers. So, 2e 10.3. On each line it will write 2 values. So, I have read xi yi and I have written xi yi on the screen. I want to write now. Where is my write statement? Write star comma 101 I write. So, that what is the advantage of this? It knows what my data are, because if I do not do this, suppose I read not from interpolate.dat, but some other file, it will be interpolating with the data that it reads. Okay. So, it is always good to write on the screen or into some other file whatever data you are using. Okay. So, this is my write statement. Now, the next two are comment cards, they are not relevant. Now, I want to define which is h. H is the spacing between adjacent point. H is equal to x2 minus x1. Remember, our data was in the class 0, 0.33, 0.66, 0.99. So, for the difference I can take the difference between any two adjacent points, okay, any two adjacent points. And now, I want to determine at how many points I want to interpolate. Remember, I had read this m is the number of points at which I want to interpolate. So, how do I get the values for the x? So, the delta x will be the final value of x minus the first value divided by real m. What is the meaning of real m? Suppose m is 100, real m will be 100.0. This real function converts an integer into a real number. So, I want to always divide a real number by a real number. It is always good to convert. The computer may still do it right, but it is always good to use the variables in the exact type that you are going to write the program for. So, now I want to initialize the diagonal difference table. What is the difference table? Difference between the value of the function at a new point minus the value of the function at an earlier point. Okay. So, I am going to diagonalize the difference table. So, if there are n plus 1 data points, the difference table will be 1 less than that. What I mean is, suppose I have x naught, x 1, x 2, x 3, the differences will be x 1 minus x naught, that is f x 1 minus f x naught, f x 2 minus f x 1, f x 3 minus f x 2. There will be only 3 differences. So, therefore, that n is n p 1 minus 1. So, if n p 1 is 4, I have subtracted 1. So, I have n is equal to 3 now. So, now I am going to calculate I want to calculate the difference table. So, before I calculate the difference table, it is always a good idea to initialize all my values to 0. So, I want to calculate this differences, but before I want to calculate, I want to set all of them to 0. So, that del y I k equal to 0. This is my initialization. This is always called initialization. It is always a good practice to initialize your variables. Okay. So, now I will generate the first order difference table. So, now look at that. Where does it start? Now, do 20 I going from 1 to n, do 20 I going from 1 to n. So, this is my difference table. Del y I, del y 1 comma I will be y I plus 1 minus y I. So, del y, the first number is 1, that means it is the first order difference. First order difference, when I is equal to 1, it will take y 2 minus y 1. So, this is the first order difference at the first point. At the second point, when I equal to 2, this is y 3 minus y 2. So, this is the first order difference at the second point. I equal to 3, first order difference at the third point. So, in del y, the first variable refers to the order of difference. So, through this particular loop, I have calculated all the 3 first order differences. So, once I have the first order differences, now I can calculate the next differences. There are higher order differences. Okay. So, what are those? Second order and third order differences. How will I calculate now? Look at this do loop. So, since the first order differences have already been calculated, in the new differences, the first variable in this del y, the first variable in del y cannot be 1 anymore, because I have already calculated the first order differences. So, now I need to calculate the second and third order. So, my do loop will be do 30 k going from 2 to n. 2 will be the second order difference, 3 will be the third order difference, and so on. So, second order and so on. So, for higher order differences, there will be less differences than the starting one. For the first order differences, there were 3. There will be only 2 second order differences. So, how do I ensure there are 2 second order differences? When k was equal to 2, that n k is n p 1 minus k. So, k is 2. So, n p 1 minus k is 2. So, there will be only 2 second order differences. So, that 2 second order differences are calculated here. Do 25 I going from 1 to n k is 2, because I have subtracted k equal to 2 from n p 1, which was 4. So, 4 minus 2 is 2. So, I am going to calculate now 2 second order differences. What are they now? Del y of k comma I, k is already 2 now, it is a second order difference. When k is 2, I want I equal to 1. So, the first second order difference will be the first order difference at I plus 1 point minus the first order difference at the ith point. Okay. So, I plus 1 will be 2 and I will be 1, and k minus 1 is 1 now. In the first loop, k was 2. So, this is 1. So, del y, the difference between 2 first order differences gives me the first second order difference, k equal to 2 at the first point. When I is equal to 2, it gives me the second order difference. So, that is how I calculate the second order difference. So, this way I have calculated 2 second order differences. My next job is to calculate the only one third order difference. So, then now k is 3. First time I calculated k equal to 2, all the second order differences. When k is equal to 3, n p 1 minus k is 3. So, n p 1 is 4, k is 3. So, n k will be 3. So, this is the third order difference. So, the third order difference del y, now k equal to 3. So, the first third order difference will be the difference between two second order differences. So, this loop, study this carefully, it gives you all the higher order differences, and once I calculate all the higher order differences, it will write them on the screen. So, it will write these are the first order differences, these are the two second order differences, these are the one third order difference. So, now when it writes on the screen, it will write a lot of data to make sure I understand what I am doing. So, I shall go here, I am going to add this thing. So, I am going to write on the screen. So, I have just typed, I went to this E, typed A, then it went to the next. Let me again show what I have done. So, I was at the character E, at that time I press type A, that means then it goes to the right side, it allows me to insert something. Okay. Then I type enter, okay. Then I want to write something on the screen. What I want to write on the screen? I will say write into bracket star comma star. So, that means I do not have to worry about format. Then single quote I am typing the difference table, okay, starting from first order, okay, single quote. So, I have inserted this line, so that now I know what the output is. Okay. So, after I come up to this, I press escape again, so that I am in the edit mode. Okay. So, through these lines, these lines, I am writing the three differences, first order difference, second order difference, third order difference. Then I calculate my 4 coefficients. C1 was equal to y1, the value of the function. The second coefficient was the first order difference divided by h. The third coefficient was the second order difference divided by 2h square, and the fourth coefficient was third order difference divided by 6h cubed. I calculate all these differences, then let me again write on the screen. Okay. I go to that right bracket, type A, then I will insert. So, I want to write on the screen, okay, the values. The 4 values of the coefficients it will write on my screen. So, this is my statement. After I insert, I again type escape. Okay. So, now let us just execute the program. So, these are all the remaining lines. What it will do now, once I calculate C1, C2, C3, C4, I want to evaluate the polynomial at those points. How do I evaluate the polynomial at those points? So, there is a do loop, I going from 1 to m. So, I want to evaluate the 100 points. So, what is the value of x at those 100 points? Real I was an integer, real I will be a real number, minus 1 into delta x. So, the first value will be 0, because when I is equal to 1, real I is equal to 1, 0.0, 1.0 minus 1 is 0, delta x is already the value I have told you, that is 0.1. In our case, I am using 0.1 for delta x. So, first value will be 0, second value of x variable will be real of 2, that is 2 minus 1 into delta x. So, the next value will be 0.1, the third value will be 0.2. Fourth value will be 0.3. Why 0.3? Because real of 4, that is 4 minus 1 is 3 into 0.1, that will be 0.3. So, I will calculate for all values of x variable the value of the polynomial. What is the value of the polynomial? It will go C1 plus C2 into x minus x1 plus C3 into x minus x1 into x minus x2 plus, see the next line, this 1 in the 6th column is a continuation. See, this is one line in this program. So, I am continuing that line in the next line. So, 1 in the 6th column, that is continuation. That is, so I have added the first 3 terms plus C4 into x minus x 1 into x minus x 2 into x minus x 3. So, these two together constitute one line. So, once I calculate the value of the polynomial, I will write it on file 12 x comma Newt 3p, this is the Newton's polynomial at x. So, there is x square and poly. So, these are the values of x and the polynomial I am going to write on the screen. Okay. So, this is my program. Then finally, that do 50 is a loop that ends, then I close unit 12 and unit 8 were open to read something. It is always good to close whichever files you have opened. Even if you do not use the close command, it will still work, but it is always good to be safe, stop and end. So, now I will escape. Okay. Now, type x, that means it saves this, okay. Enter. So, I have saved whatever little changes I have added. Now, I will compile. How do I compile? G Fortran intrpn dot f. So, I am compiling this particular program. Okay. So, it has compiled without any error. Now, I will execute. How will I execute? Through a dot out. Now, look at this. The a dot out here gave you a time of 15.01. So, this was before I compiled. After I compile, this will be a new a dot out. How will I know it is a new a dot out? You see the time. This was 1501. So, let us do ls minus l, enter. You will see that it shows 1531. So, the time 1501 is replaced by 1531 because it is a new file. All other times are the same. See this argon 2057, 2057, argon.f 2114, 21. It has not changed, and interpn.f, this was at 3 p.m. So, since I saved it again, you see that interpn.f, that is 1531. So, since these two programs are new, the times have changed. So, that means the old values, old files have been replaced by the new files. So, this is one way to know. It is always good to take screenshots if you want, and whenever a program is changed by the new times, you know that the program is a different one. So, I have compiled, this is my new a dot out. So, therefore, this another good point is whenever you have an a dot out, you do not know which a dot out it is the new one or the old one. So, it is good to keep track of them. I will execute now dot slash. So, now the moment I execute, it is executed. So, what it is doing? First, it is writing all the values of xi and the values of the function. Remember, I mentioned to you, it is always good to write whatever you have read on the screen. So, it has read the values of x 0.333. In our class, we did 0.33 and 0.36. Here, I have done a little better 0.333, 0.666 and 0.999. These are my values of x. These are my values of y. Remember, it is an E format. What is the meaning of E format? So, there are total 10 spaces. Okay. 1, 2, 3, 4, 5, 6, 7. Okay. E plus 0, 0, that is 4 values. These 3 zeros, that is 7 point, and this 0. So, it has taken 10 spaces, the first one and the next 9. For the second one also 10 spaces. Which are those 10 places? The blank one 0.100. So, these are 6 values plus E plus 0 1, 10 points for the second, 10 spaces for the first. It is all the values of xi and yi. Now, remember, in the program I added this line, the difference table starting from the first order. So, I have a first order difference, I have a second order difference, I have a third order difference. In the class, I wrote as columns and rows. Now, these is my first order difference, second order difference and third order difference. So, these are the 3 differences. Then I also have typed in the program to write all the values of the coefficients. So, these are the values of the coefficient 1, 1.17, 0.6898 and 0.478. So, these are the 4 values of the coefficients. This 100, 0.33 and 99, let us find out after some time what these are. Now, see, since in the program I did not ask it to write what this is, I have no idea what this is. So, I have to go back to the program and check that line. So, before I do that, let us see what are the results now. So, the results were put in NI, NEWT, INTP. This is the output file. So, let us edit that VI, NEWT, INTP. So, I am going to see that file. This is a file in which all the interpolation data that I created is written. So, what will it write? So, look at the first line x comma NEWT 3 POL, value of x and the value of the polynomial 0 and 1. My first value was 1, x was 0, y was 1, and in my data after the first data of 0.00 and 1, my next data point was 0.33. See, this is the next data 0.33 and 1.4 was my value of my function. So, it has calculated actually in my function I had value for 0.333 and a value of the function. In the interpolated values I have 0.33 and 0.34, there is no 0.33. It does not matter because my polynomial calculates for all values of x between 0 and 1. So, you see that my input data was 1.39 at 0.33. So, you see that all the values lower than 1.39 are for values of x less than 0.33. So, values of x goes from 0, 0.1 up to 0, this is 0.01 up to 0.1, then 0.2, 0.33. Okay. So, these are my values of f x. So, let us see the remaining values as I go down. So, my last value is 0.99 and the value of the function is 2.71. So, this is my interpolated polynomial, this is my independent variable x. Now, you will see that instead of 0.99, my value of x that is written is 0.9899995. So, as far as we are concerned, it is a recurring 999. So, instead of 0.98999, I can read it as 0.99 as well. So, this is my interpolated polynomial. So, before I go to the Lagrange, let us find out what that last line was. Okay. So, how do I come out of this? Shift colon q factorial. So, I come out of this. So, what I want to know, see, remember the program wrote 100, 0.333 and 9.99, 10 minus 3. Let us see what this is. So, I will go to VI. I go back to that program and see what was that last statement. Okay. So, here is that statement. Okay. Remember, we wrote C0, C1, C2, C3, C4 and then it wrote M, H and delta x. Okay. What it wrote? M was 100, H was 0.33 and delta x was 0.01. 0.01 is spacing. Since I have 100 points, I have taken delta x to be 0.01. So, 0.01 into m will be 100. 100 points are there. I am calculating the 100 points with a spacing of 0.01, that is 0.01, 0.02, 0.1, 0.2. All the 100 values of x are obtained by multiplying delta x to that 100 values. Let us look at that again. See this, my real I goes from 1 to 100. So, 100 into delta x will be, last value will be 0.99, because the first value was 1 minus 1 into 0.01, first value was 0. So, the 100th value is 0.99, that is the value at which I calculated my Newton's polynomial. So, now what I want to do, let us now look at Lagrange method. So, Lagrange method, I have already enter PL dot F. Okay. Now, see, this is my program for Lagrange's interpolation. All the things up to this delta x are the same, okay. Same input files, same dimensions, everything is the same, except now x variable, okay, will be x1, that is my first value, which was 0 plus real L minus 1 into delta x. So, x variable is the same. Now, I want to calculate LKX and LK together. Okay. So, look at these lines, do 20 I going from 1 to NP1, term equal to 1, do 15 I going from 1 comma NP1. If I is not equal to k, okay, then term is equal to term into x variable minus xi into xk minus xi. This is exactly, when I add all the terms, it will be yk, see this is yk into lkx divided by lkxk. This is exactly the same as the formula I have shown. So, this is my Lagrange interpolating polynomial, it will calculate in exactly the same way. So, I will, this program is available to you, I want you to practice it, I will come out. So, I will compile it. Interpol L dot f. So, this is my Lagrange interpolating polynomial. Okay. I am compiling the Lagrange one. Okay. When I type this A dot out, it is the Lagrange one that is executed. Okay. This is executing. Okay. So, we will view the output. So, before I view the output, let us do Ls minus L. Now, you will see that the A dot out corresponds to 15.41, earlier was 15.31. So, this is the new A dot out, which is the execution of the Lagrange interpolation polynomial. So, to find the results, my data file is not changed, I have called it NEWTINTP. So, VI, I should have actually called it with a different name, NEWTINTP. So, I should have called it Lagrange interpolation, but I have not changed it. Okay. So, these are now the values of x and the values of y. So, here I have called it, instead of Newton interpolation, Lagrange third order polynomial. These are the values of x and these are the values of y. So, you will see that both programs give exactly the same result. So, now let me conclude what I did in today's lecture. I executed the Newton's interpolation polynomial, I executed the Lagrange interpolating polynomial, both gave me 100 values between x0 and x1. Any other method also will give you the same result, because this is a unique interpolating polynomial. So, in the next class, we will see what are the errors in these polynomials and then finally go to matrix methods. Okay. These matrix methods are very important in chemistry, because it helps you to calculate eigenvalues and eigenvectors of your Schrodinger equation. So, I will conclude here. Thank you.